actually believe, which will take more time than the wind tunnel. And there's the ones you don't believe at all, but we can do them really quickly.
Yeah, I mean, there's those little metal parts.
And the second team's got a lot of work to do. They don't,
Yeah.
they don't understand what they're doing.
Those
They don't know how like that.
3 millimeters.
Good luck. What's that?
Interesting to see what they end up with.
Yeah. All right, guys.
Very well today, right? Yeah, it's alright. Looks like we
Definitely aren't strong enough.
Alright, well, that's why we upgraded the arms.
So no crashing.
Got it. Greg, don't crash into carpet. No, you're fine. No, you're fine. Yeah.
How about that last one?
But do you want to just bring that back upstairs?
Oh, yeah.
Sorry.
No, you're good, sure. You're good. It's, I'm keeping this one out there just for like, I need something to reference as I frantically CAD more of these.
Okay, so let me start by talking about some logistics. So I realized that because of time, I need to change the content in the lecture just a bit, just cut something off. But the main thing about expander should be there. But because I changed the schedule a bit, that is why these remaining lectures, I just to be fair for everyone, I just remove everything and you just put your name again. These are the topics that we will be talking about. And by the way, this one might be easy to scribe, very short too. You can put your name too. So easy way to get points. But even with this, it seems that not too many slots, too few slots anyway, for for everyone to scribe. So here is an alternative. So basically, you can put your name in the editor column, which is here. Basically, like for each of the lecture, you can put your name here. And the task is basically simple. Basically, if you edit like 3 scribe, then it's the same thing as writing 1 scribe, and the grading is still the same. Like basically, if you don't have your own slot for writing scribe, you can edit it instead. And the task is just to read through the scribe and just try to improve the quality when you see what can be improved. Like add some clarification, add picture, fix typos, and so on. Yeah. And if there are more serious issues that need some like you can try to handle things by yourself, but if you want to ask the writers to fix something because it requires too much work, you can like add some comment like this. Like for example, using this code, you can add a comment like put like a comment saying that you put some comment like you type like here and add something here. Then like here I put some comment here and it will appear something like this. Just add a comment if you cannot fix it yourself. And once you edit things, you can just send a brief email. How did you edit? I can look at the history anyway. So I hope it makes sense. Okay. And problem set. The problem set 3 will be out soon. I try to like really not like make it not as hard as the previous one because it seems I really skipped some step in the previous one. And the problem set 4 will be there too, but it will be very short, like maybe 1 or 2 or 3 problems. For the exam, because we just have very few students, like 12, so let's do oral exam. It will be 20 minutes, we assume. Maybe between 16 and 17 December, you can just like I will create some schedule and you can book your time later. Yeah. And the point of the exam is not to like it shouldn't be stressful like problem set. So basically, just to check that you understand the material, you will not need to solve any new problem. I will just ask you about something which is there in the material, either lecture note, but maybe something in the problem set too. So, like I just ask like, what is that? What is the? Why is that important? What does it mean there? Something like that. Yeah. So, and because of the time constraint, I will need to omit some material which is very cool. It's called multiplicative weight update. Like actually, it's a very cool algorithm. If I have only one, like can teach only one thing in my life, maybe I teach this thing. But we don't have time, which is pity. But I teach this thing in previous course already, so you can have a look there. And there are many good material online. So. But we will still need it. So in the last lecture, very last lecture, we will use this thing as a black box. I will just state this black box. But if you want to know what is inside the black box, you can also, like for example, go to my lecture or read this paper. Like it's gonna be like just a few pages. Okay, so any question about logistics? All right, then we talk about push reliable again. So, okay. So last time we talked about push reliable algorithm, and the algorithm is quite actually simple. First of all, the algorithm, like you are given a graph, and then you're given a source function and a sink function and parameter h, right? And the thing that the algorithm maintain is a preform and a vertex level. And what we have is that basically the algorithm transform valid state to valid solution. And valid state is like we said that F and L is a valid state if two things happen. That is, for any edge that skip the level, you know that the flow is saturated from U to V in like a downward direction for any skipping level edge. And also for any vertex that have level more than one or at least one, then they are fully absorbed. Okay. And then at the end of the algorithm, we will also make sure that like this is the thing, this two property is the thing that the algorithm will maintain throughout all the step. But at the end, we will have that the algorithm will be a valid solution, which just means that like every node here that have level less than h will have no access. Okay, so that's what push reliable try to do. Okay, and we have described the algorithm. The algorithm is that you just, okay, maybe just look at this. The algorithm is given this thing and all the input. What it does is just keep finding an active vertex, right? And by active, it means that the level is less than h and it has some excess. The goal is really just look at the guy that have excess. But if the guy have level h already, then we give up on that. Any guy that is still have excess, but still have excess, but have level less than h, try to remove excess from that node. So choose the active vertex U, and try to push or relabel U. And what is the condition? Basically, if this is U, then you try to look for the admissible arc or admissible edge at U. And so that is, you look at the residual graph, right? And if there is an edge in the residual graph that have residual capacity more than 0, and the node, another endpoint is level below. Like 1. This is level I, this is level I minus 1. If there is such an edge, you push. Otherwise, if there is no such edge, no admissible arc at all, you relabel. Yeah. And so if there is such an admissible arc, then you push, and you will push something more than 0, right? And by pushing, it means just sending flow from U to V by this amount. And how much is that? Like, it's just try to send as much as like a minimum of your excess or the residual capacity along that edge. Okay. So, and if otherwise you label, it just means that you increase the level of the node. So that's the algorithm. Okay. And we have seen the proof that, okay, indeed, the algorithm really just maintain like F and L is valid throughout the algorithm, and at the end, F and L will be valid solution. And also, so the algorithm is indeed correct, and we also have bound like the number of operation that we call like. So can you recall how many Lie-level operation we do throughout? Like for each node, how many times you can Lie-level? Each time, yeah. So basically, the total number of Lie-level is at most n times h, because the level only increase. And so also we have like to bound the number of push, we separate two type of push. One is a saturating push, meaning that when you push, like after pushing the edge that you push along the flow, that you push the flow along, becomes saturated. So how many saturating push we can have? Like for each edge, how many times you can push saturating push from U to V?
Once. For each edge once.
Say it again.
For each edge once, right?
For each edge.
One.
Not just once, but it's gonna be something like, because
H into H times, right?
Yeah,
Because it keeps.
yeah, H over 2, right?
Yeah.
Yeah, because when you push in the saturated way from U to V, you might need to like you need to push from V to U again so that you can push from U to V again. But in order to, if you want to push from V to U, it means that the level of V need to be increased by at least 2 before you do that. So that's why in one direction from U to V, you can saturating push from U to V at most H over 2 times. So now if you sum for both directions, and H is H, and there are like M edges, so the total number of saturating push is MH. And then, so that is like one thing we bound. The harder thing that we use, like the harder thing to bound is the number of push which is unsaturating. And to do that, we use some potential function, and we show that each of the unsaturated push decrease this potential function by at least 1, and everything else can increase this potential function by not too much. So that's why you can bound the number of unsaturating push. So that's the strategy that we did. And when I said that everything else can increase this potential function by not too much, in total this is something like mh squared, which is why the number of unsaturating push is at most nh squared. Okay, so that's the recap. Okay, now so far we just bound the number of push and Lie-level, but we didn't really say about how to implement the algorithm really to like, there will be some implementation detail. For example, there are two things to implement. Like, recall that the main while loop of the algorithm, you just keep asking, give me the active vertex, right? So you just need to get this one fast. Okay. So that's one thing to implement. Like, we need some data structure for it. Another thing is, when you set up, you get an active vertex U. Let's say this is U. Now, in order to push out to the level, we need to look at the admissible edge, right? So if you do it trivially, you need to spend like degree time for every time you want to check. You read all the edges along the, like, throughout incident to this node. But we don't want to just read like the degree, like spend degree time for every time we look at you. So we need to handle this thing too. Okay. So now the first issue here is gonna be very simple to handle. Can you like try to suggest what to do just to get some active vertex?
Binary search tree like data structure.
Yeah, that would work. Just explicitly maintain the set of active vertices in some list or some dictionary. Actually, just put it into a queue. We don't even need BST. Put it in some queue, and maintain that list, and then just get the first guy in that queue whenever you want it. That would be fine, right? So nothing to be very simple to take care of this one. And for the second issue, here is the simple observation that will help. So look at this. Suppose that U is here, and suppose that, okay, V1, V2, and maybe this one is not admissible anymore. So this is in the residual graph, okay? So suppose that this one is still admissible, like the residual capacity is still more than 0, but some of them is not admissible. Like maybe some of them is not even like in the downward direction. So note this: when some edge is not admissible, it can only be like it will not become admissible again. As long as a vertex, like as long as you don't relabel U, right? Why is that? Well, like if the label of U is fixed here, if the label of V increase, like maybe here, then this edge will not be admissible from U point of view anyway. Like, or like only like think like maybe this edge, maybe if you actually increase its level to here, maybe now the edge looks like this. Now this edge become admissible, but if U doesn't increase its level, any non-admissible edge remain non-admissible. Okay. So once you know this, it means what? It means that actually, like, what you can do is for each node u, you can just maintain some order list of your neighbor, like just sort in, like put you out of your neighbor in some list that is ordered. And whenever you want to find admissible edge, you can just look through your neighbor in this list. If this neighbor is not admissible, you know that you don't need to look at this guy again, right? It will not be admissible as long as you don't increase your level. So as long as the level of node you remain the same, you know that you need to scan through this list only once. Like the total time to look for the admissible edge is just degree of u in total, as long as you don't increase your level. Does it make sense? Okay. So yeah, so you have this order list, and you have maybe like a current neighbor that you want to look at, and so basically when you call push relabel at u, just look at node u and your current neighbor of u. If it is admissible, just push along that edge, and that is a push operation. If it is not admissible, then you update your current neighbor to the next guy in the list, right? And if the current neighbor is already the last one, now you know that nothing is admissible, so that you can relabel, right? So to conclude, it means what? It means that before relabel, u is called before you increase the level of u. The total time that you spend to look through this, to look for admissible edge is the degree of u. So let's charge all of this cost to relabel, right? Like the time that you spend to this, you can charge it to relabel and think of the operation of relabel as like the cost for relabel is like degree of u instead of just one, because you charge this cost to the relabel. And if you charge the cost in this way, we can say that the total time of relabel is summing over all nodes, and each time you spend degree of u time, and for each node there can be at most like h relabel. So the total time for relabel is mh. Okay. So basically, just to say again, like to get this admissible edge fast, we can maintain this order list and charge the cost for listing this thing to relabel, and the total cost of the relabel is then like mh. Make sense? Okay. And like the real cost of relabel is nh, right? But here I just charge the cost of listing this thing to relabel. Now it's mh. And for the cost of pushing, each push just really takes constant time. So saturating push is mh, unsaturating push is mh squared, so the total time is this. So the bottleneck is still this guy, really. Okay, question about the time complexity?
This is mh squared height, right?
One can improve it, yeah.
I'm
Like-
following this algorithm. Like, is there some input so that the running time is mh squared?
Yeah, I think so. Yeah. the total number of push, unsaturating push can be as large as this. But if we have time, I'm gonna talk about how to improve this running time. Okay, but let's look at, so now we have seen how to, like, given any valid state, you can make it a valid solution. So let's see application of this. One is MaxFlow. So what I will state as a problem will not be exactly MaxFlow, but if you can solve the following problem that I will state, you can see that you can solve MaxFlow using some binary search. The problem is here. You're given graph and sink and source function. And what you need to do is either find a feasible flow certifying the sink and source. Do you recall what it means here? So can someone tell me what does it mean by F certifying this?
And it's between 0 and t, I guess.
Yeah. For all. And F at P is defined to be the initial mass at V plus the total flow into V. So this is what it means by a flow certified source and sink. So you either find a feasible flow that certifies source and sink, or you just say that there is a cut such that this is the case. Like the initial mass, even after you subtract what you can absorb in this cut, it is still bigger than the cut size. And this really actually is just a way to, it's just really a certificate that no such flow in the first case exists. So basically the algorithm is either find a feasible flow or saying that no feasible flow exists. And in the second case, you just return this certificate as a cut. So now the algorithm is very simple. Just call basic push label on the input, and you set the h to be n+1. And when you call this, basically you will get F and L, which is a valid solution, right? And there will be like two cases. Basically, the case when there is no excess, which means that there is no vertex at level h. If there is no excess, no vertex at level h, then everyone have excess 0, right? So there is no excess. Otherwise, there will be some excess if some guy is at level h. There's just two cases here. So let's look at the first case. Well, when there is no excess, it just really just means that F is a feasible flow. So we are done. Yeah. And what we need to show is that actually if there is some excess left, then we will actually construct the cut that we claim here. And so let's try to construct such a cut where this is the case. So the important insight, which is that we will use is here, because h is just more than the number of vertices. There must be some level such that there is no vertex in that level. Let's say that, so h is here, which is n+1, this 0. There will be some level k where like nothing is here. There are some vertex here, but nothing is at level k. And now what I will define is just define our cut S. Our cut S is just all the vertices here that have level more than k. This is our cut S. And the first thing to note is if you look at the total flow out of S, this is going to be exactly the cut size. Why is that the case? Like,
Because flows cancelled.
I don't think that is quite the reason. So if you look at the edge that go out of this cut S, right? It must be what? It must keep the level. Yeah. Like if this is level k plus 1, this is going to be at most k minus 1. So every edge going out of this skip level. So the flow here will be saturating. So it means what? Just take all the edges going out of this. The total capacity here are saturating by the flow, which just means that the flow out of S is exactly the cut size. Right? So keep that in mind. Yeah. And now we're gonna look into, like, we will analyze things a bit more. So keep this in mind. If you look at any set S, we discussed this in the previous class. If you take any S, you can just write, like, say that the initial mass that originate in S, this is the initial mass in S, can either go out of S or absorb inside S or remain as an excess in S. That's the only, like, 3 choices that can happen for each unit of the mass that originate in S, right? So we have this equality, and now let's analyze it one by one. This one is the cut size, and let's look at the absorbed. Why is the case that the mass absorbed in S is exactly the total sink capacity in S? Well, because every guy here has level at least 1, right? So, and our solution is a valid state in particular. So everyone here, like, is fully absorbed. So every node U is fully absorbed, and this is true for all U in S. So the total absorbed flow is the total sink in S. Right? So this is T of S, and the total excess in S, well, we actually know that this is exactly the total excess for the whole graph. Because why? Because the excess can only be in the top level, actually. So, and the NS actually contains this top level. So actually we have that this is the excess is all the excess is at the top level, and this is more than 0. So this thing is more than 0.
Can it be the case that the top level can also have 0 excess?
No, because when the reason that we move thing to the top level is because it is active, and when it is active, it has some excess, right? When you move there to the top level, you don't touch it ever, so the excess remains there. Okay, now with this equality and like just by plugging everything here, you have that this thing is here, this thing is this thing is this, and the excess is more than 0, so this is strict. Which is what we want. This is just saying that the cut size, one sec, no. Yeah. You have this, right? The total mass, the total initial mass, even if you can absorb everything, is still bigger than the cut size. So that certifies that there is no feasible flow. Okay, so that's the max flow. So this gives basically mn squared time max flow algorithm. Actually mn time algorithm for solving any sourcing function, and you can use it to solve max flow. Okay, next is how to use it for finding sparse cut. Okay. Well, you see, the time for solving max flow here is quite slow because you set h to be n. But for finding sparse cut, we will actually set h to be something like polylog. When phi is 1 over h is going to be something like n over phi, and this is usually polylog. Yeah. So it's going to be fast. Yeah. So what is this subroutine? You just need to recall what we talked about when we try to use a cut matching game for finding sparse cut in the graph, right? The step that we will need is the algorithm for the matching player, that given a graph, given A and B, you either kind of embed a matching from A to B, or find a sparse cut. That's the subroutine that we want. Do you recall this roughly? Okay. So specifically, the problem is here. You're given a graph, and you are given A and B, and the volume of A is less than the volume of B, and some parameter phi. And we want to find a cut which is sparse. Otherwise, we will embed phi a matching M. Actually, not quite matching, but it's a bipartite graph such that each node, it's a B matching, where the B vector is the degree of a graph. So if recall that if we talk about expansion, then we will try to embed a matching. But here we try to, instead of working with expansion, we want to work with conductance. So we will need to adjust the subroutine a bit to talk about, instead of matching, we talk about a B matching, where B is the degree vector. Okay, so we want to find this this B matching M of size volume of A, and this M should be embeddable into G with this congestion. Okay. A question about the subroutine, the problem that we want to solve. Okay. So now the algorithm is here. So it's quite natural what to do. Like we have A and B, and we want to send flow from A to B, right? So what we do is the source function is just that, and each of this guy basically want to send degree of U flow, unit of flow from each node U. So anything in A, you set the source to be degree of itself. If U is in A, set the source to be degree of U. And for the guy in B, the sink is a degree again. Okay. So TU is degree of U. So this means that if you find a flow that satisfies the source and sink function, then it really corresponds to this graph M, where the degree of M of everything in A is degree of like the degree here, and the degree of B is at most the degree of the graph. Okay. And then the graph that we actually will be working at is just, I call it GC, which is the same graph G, but you set the capacity of everyone to be 1/5. And that makes sense, right? Just because the congestion that we want to embed the meshing is 1/5. Okay. And then we just call this basic push label on this input. And you set H to be this much. So think of this as something small now. So that's the algorithm. And well, the correctness is simple again. Like there are two cases, either there is an excess or not. And if there is no excess, then you get a feasible flow. That's really the definition. No excess, you get a feasible flow. That satisfies source and sink. But we just really define source and sink and the capacity in such a way that this flow would correspond, like the flow itself is an embedding of M. Yeah. Okay. So if we get no excess, then we get the matching M. Yeah. Otherwise, if there is some excess, then we will try to construct a sparse cut. And so how do we construct a sparse cut? Well, we look at like this level again. Like, so we basically look at the level of vertices here. And when you use when you use push and relabel to find some cut, it's always like this. Like it's always find some cut that is like a prefix of some level. So and so basically now, yeah, S will be a level cut where like it contains all nodes with level at least k for some k. And the important step that I want to claim is here. So in the previous case, we said that when h is big, like n plus 1, there will be some level such that the flow out of it is exactly the cut size. Right? We used to have this thing. But now we want to be more efficient, and we set h to be something much smaller. But we want to say something similar. That is, there is a level such that the flow that go out of this level, the total flow go out of this level, is basically almost the cut size, but minus something, which you think of something small. Okay. So it's like it's a level here such that most of the flow actually is saturated, except there are some like edge that is like small part of it which is not saturated. Okay. And to be more specific, I claim that this thing is basically at least the cut size. Okay. Know that we work in GC, right? That's why it's a cut size in GC. Minus this term. That depends on the volume of a cut. So if this is the case, then I just like because GC has capacity 1/5 per h. Now this thing is exactly this thing. So everything is just scaled by phi. So let's try to prove this. Actually, let's assume this and see why this is useful. Okay. There is a level where like almost all of the flow is saturated except small thing. So okay. So once you find such a level such that the flow is like almost saturated, that you have this thing, then let's set S to be such level. Okay. And recall that you have this equality, right? And what is this again? This thing is the same reasoning. The total absorbed flow inside S is the total, like S is fully absorbed, so absorb of S is a sink of S. And this thing is more than 0 too. So you would have this. Okay. But this thing is gonna be less than the volume or the other side. So why is that the case? Like one case is easy because, well, can you see why this thing is less than the volume of S? So like you have A and you have B, and if this is S, then if this is S, then the total source of S is here, like from here, right? But each of this guy the source of this guy is degree. So the total source from S is really just the volume, like the total source from S is really just the volume of S intersect A, which is at most the volume of S. Okay. And if you even minus this thing, is still like less than the volume. You can show that like this whole thing is less than the volume of the complement too. It's gonna be like not hard to show. Really just kind of look at the definition like this again. And so it's I will just keep that. So what we have here is that this part is less than the mean of volume S and volume of the complement of S. But at the same time, we have that the flow going out of S is something like this thing minus mean volume S here. Now when you just change the size of inequality, actually I put it something like this. Just combine these two inequality together. Well, then you have that the cut size here is less than like 1.1 times phi of the volume. Okay. So what we really just need to show is that it's really here that similar to the max flow case where we said that there is some prefix, some level cut where the flow is saturated out of it. You just prove something similar, saying that most of the flow is saturated, except like most of the edges going out of it is saturated by a flow, except something small. Okay, so let's prove this. Well, so how to prove this? Well, just let's look at the graph that I call G-con. That is just a graph, GC, that contains only edges between consecutive level. Okay. I really just look at the graph, like I draw the graph into level, and I only take edges between level. Remove all edges that skip level. That's G-con. And now, the claim is that if you look at this graph G-con, there must exist a level that is quite sparse in this sense. Like there must exist a level, some level K here, such that the total number of edges here, the cut size, the cut edges is small compared to its volume. And this is quite simple, like it's just a ball growing argument. So why is that? Like why there must exist such a level such that the cut size is maybe like 5/20 less than this? Because look at here, like if you just let's say that suppose that, so you look at each level here, the volume of level, like if you look at this level and the cut size here, the volume of the next level, this thing, is at least the cut size plus the volume of the previous level. Right? But if this thing is big, is phi fraction of the volume here, then this is gonna be growing by 1/5 factor of the previous layer. So if every layer is not sparse, then it means that each time that you look into the next level, it grows by 1/5 factor. But this cannot happen. This cannot just keep happening, right? Because if you look like from h level into h minus 1 level, and that none of this is like not sparse, like there's no sparse cut at all, then the volume here gonna be at least 1/5 to the I. But if you set if I is something like log n over phi, or like 100 log n over phi, this is gonna be already like n to the 10. But then that's a contradiction already, right? So that is why, like, if you look into this graph G-con, there must exist a level which is sparse. Okay. So just take that level. Okay. Let's say level K is sparse in G-con, consecutive. And now, so okay, we have level K such that the cut size is small. By small, I mean phi times 20, phi over 20 times the volume. Yeah. So it's sparse, but just by doing the same argument from both sides, you can say that this thing is less than like the volume of both sides. By the way, like G-con is a subgraph of GC, so you have this too. This is GC. Yeah. So now observe this. We are almost done now. Why? Because if you look at the level K that you choose here, the edges outside G-con are the edges that skip level, right? So basically everything outside G-con that go out of this cut are saturated, and there are some guys that are not skipping level, but they are here in G-con. But these guys are small compared to the volume. So we have what? We have that the flow going out of this cut is basically full, except the part which is from G-con. Make sense? Why there is factor 2 here? Because like this thing count each edge, which is from a consecutive level in one direction, but the flow might go in the opposite direction, right? So we get like a factor of 2 for each of these edge. Okay, so this thing is basically like phi over 20 times volume. In GC. So which is what we want. So quick question about this proof. Are you with me, or this is which one is which step is not is confusing? It looks like everyone is confusing, so you need to ask question.
Can I ask some question about
Yeah.
like the algorithm? Like, so you initialize the labels of the vertices in like A side and B side, with the A labels being equal to H, and all the labels on the B side equal to 0. Do those labels changes during the algorithm?
1 second. A and B has nothing to do with the level.
Oh,
So A and B really just specify how to define the source and sink function. You define every guy in A to be source, like each guy in A to send the mass of degree, and every guy in B to absorb the mass of degree. So that's just the only thing about A and B in our algorithm is specify how to define source and sink function. And then when you run this push level, any node can be in any level.
so we start from all zeros,
Start from all 0.
and we only increase that whenever,
Yeah,
and until they hit the height limit.
right.
Thank you.
Yes. Sure. Okay. More question. No question?
I have a weird question.
Yes.
What's like the intuition of this pusher label thing? Like, what's the sort of key idea that lets you apply it to these sorts of flow problems?
Yeah, so the key idea is that let's see. Like why I use it for sparse cut, you mean? Like why, like morally, why is it a good choice for finding sparse cut? So this is the key idea here. Like the point that we can find, like once you, like first of all, if you have any graph such that the edges, like if there is some arbitrary graph such that there are like edges are layer like this, like you have a layer of nodes and edges are only between consecutive layer, you know for sure that as long as the number of level is more than log n over 5, you know that there is a sparse cut in the graph. Right? Just look at each level. One of the level must be sparse. Really just by using this argument. So this is like a structural lemma that you know. When you have just not too many level, there must be a sparse cut. Like once there are log n over 5 level, you get a sparse cut. And now push the level really give you how to arrange vertices into this layer. And
Can I think of it as like sort of some like weird BFS where you sort of like BFS also kind of has this weird property, right? Like edges are between.
Yes, yeah. So very good. So when you do BFS, you will get layer as well. The nice thing about push level is that you get this layer, except that like the edge that skip level, they are kind of done. The edge that skip level, they are saturated anyway. And you you are done with it in the analysis. And the guys that are not skipping level, you can find a layer that is sparse, that are not too many of them. And by using that and combine inequalities, then you get sparse cut. I hope that's not too high level. Yeah.
No, that was really good. Much more helpful than sort of going. I don't know. I've gotten lost in the symbols, to be honest.
Yeah.
Quite like curious, like why do we have like a 5 in the denominator? Like what happens if we want to pursue like something better than 1/5? I'm not sure.
Why you ask why the number of layer is this? You mean? Or why you set the capacity to 1/5? Which one?
The goal for setting these parameters is because we want to either find a matching a flow value at least like 1/5 or we do have a cut, but they are having like a gap like 1/5 between these two. Right? Is that?
Not sure if I understand the question. So we want to embed a meshing with, I see.
Is there any intuition like for that 1/5 there?
Yeah. So let's see. If suppose that there is no sparse cut. Suppose there is no sparse cut in the graph. No phi sparse cut in the graph. Then you know that you can always embed a meshing and with conjunction 1/5. Like if there is a sparse cut, phi sparse cut, you know that you cannot embed a meshing like with conjunction better than 1/5. So that's how like like if there is some sparse cut, like which is kind of phi sparse. So what I say is not like quite the case. What I can say is just that not about embedded meshing. I can only say that if there is some phi sparse cut in the graph, you know that you cannot embed expander with conjunction better than 1/5. Yeah.
So in particular, like this matching is the best we can hope.
Yeah.
Sure. Next. Sorry.
Okay. So now so this is like, so now that what we got here is that we can either find a sparse cut or embed a meshing. So this is really just a step for a meshing player when you apply a cut matching game. Like when we want to find when you want to find some phi sparse cut, you just call this thing log n time or log square time. What if you want to find a balanced sparse cut, right? We look at like kind of a similar variant of this problem where it either find a balanced sparse cut or embed a meshing with some fake edges. So the problem is like, do you recall this problem? Like we have a graph and A and B, and we want to find a sparse cut here, but your sparse cut must be balanced. you must embed a meshing M prime, but with some fake edges. So this thing is just the same as M in the previous setting, but there are some fake edges that you don't really embed. Okay. So you embed the M prime into the graph, but the M prime union with F is the meshing from previous case. Okay. So this is just another algorithm that if you can solve this one log square time, then you can use this as a subroutine in the cut matching framework to find balanced sparse cut. Right? Just need to recall the previous lecture. And balanced sparse cut is very useful for expanded decomposition and so on. Right? So this is why we want to solve this. But we can solve this using basic pre-flow push, using the same algorithm really, exactly the same algorithm and analysis, except that we will change the threshold. So if instead of the threshold used to be 0, now you change the threshold to be beta. If the excess is less than beta, it means what? It means that you almost embed the meshing that you want, except there are beta unit of flow that doesn't send from the source to sink. Right? If you send all the flow, you get that meshing. But there are beta unit of flow that does not send from sink to source, from source to sink. So it just means that this thing, if you apply the flow path decomposition in this flow, in this pre-flow, then you get M prime, which is almost the same as M, except that the size is less than M by beta. So you get this M prime. But if the excess is bigger than beta, then now we will also show that the cut actually must be big. And why is that the case? You will just use exactly the same analysis, use the same algorithm for finding sparse cut. Now I claim that that same algorithm will return you the cut that is balanced. Why is the case? Well, we have level of layer of graph, right?
Yeah.
But now we know that the excess is big. The total excess in the graph is big. Where can the excess be? Only at the topmost level. And for each of these guys, the excess at each node here is at most the degree. Right? Because the excess is at most the source, but the source is at most the degree. But the total excess here is at least beta, so it means that the total volume of this whole thing is at least beta too. Okay. And your cut here must contain the topmost level. So your cut is at least as big as beta. And you can actually prove using the same similar analysis, saying that the bottommost level, also the volume here must be as big as beta. We will show this maybe in the exercise session, or you can think about it. But because the bottommost level is at least beta 2, then S bar must be as big as beta as well. So the same algorithm, just change the threshold of the excess. Okay. So I'm out of time. So to recap, the running time that we have so far is like mh square, which is mn square for MaxFlow and this much for finding sparse cut. Actually, one can improve it to mh log n using dynamic tree. And normally, I don't see any class that teach this, but because this is an advanced class and everyone should know about dynamic tree at least once, so I would teach it. But we are off time, so I will just record the video, and this is not, you don't need to look at the video before Thursday, because we're gonna talk about local and dynamic version of push level, another advanced technique for push level. But I really want to suggest you to look at the video, because dynamic tree is very powerful and you should know about it once. Yeah. At least seen how to use it at least once. This is the use of dynamic tree is really the first application of dynamic data structure for fast algorithm. It's really the first thing that generate this field of dynamic algorithm. So yeah, we will see it in the video that I will record it maybe today. All right, any question before we stop for today? All right, then see you.
I will be subscribed to
Yeah. Right. So maybe just write your name in the some other slot. Yeah.
All right. Yeah.